let's take a look at number 1 as we develop this idea of a slope field. So we have this derivative dy dx equals 3x squared, and the solution to that is y equals f of x. Now we're not going to find that just yet. We're going to analyze what a curve might look like if it had the derivative dy dx equals 3x squared, or in other words, using different notation, if f prime of x equaled 3x squared. So the slope here depends only on the x. So let's take a look at the slope field. So if I wanted to know what is the derivative or the slope when x equals 0, then that's obviously 3 times 0 squared, so it's simply 0. So now I'm going to come over to the slope field and show that if the solution, y equals f of x, passed through any point where x equals 0, then the slope would be 0, and I show that by putting this little horizontal slope equals 0 slash through all the points where x equals 0. Alright, so let's take a look at the next one. Let's say f prime of 1, and all points where x equals 1, the slope will be 3 times 1 squared, or the slope will be 3. I'm going to do my best to illustrate a slant or slope of 3, up 3 over 1, so kind of like that. Yeah, it looks pretty good. Alright, so at all points x equals 1, the slope would equal 3. So if the curve passed through any one of those points, it would have a slope of 3. Okay, continuing on, we have f prime of negative 1, and you see that will also be 3 because the negative 1 is squared. So those little slashes are parallel to the ones we just drew. So I'll try my best to make those same slope slashes like that. Okay, a couple more to do. We have f prime at 2 and f prime at negative 2, and those will both come out to be 3 times 4. Those will both come out to be 12. So once again, come over here. It's a little hard to draw this. Up 12 over 1. Let's just say that's really steep. So, alright. I'm trying my best to make it parallel to the one before it. And these will also have a slope really steep of positive 12. So that completes our task for part A, which is to make the slope field. In part B, it says, what if our solution curve y equals f of x, what if that passed through the point 1, 2? So that point on our graph, 1, 2 is here. And what if our solution curve were to actually pass through that point? What would it look like? Well, this gives us a sense of its contour. So if I start here, we know it's going to get steeper as it approaches 2. So let me just kind of come down like here. The slope will be here, and then it'll have a slope of 0, and then it'll have a slope of 2, and then it'll get really steep and go down in that direction. Over here, same thing. It's going to be positive and get steep as it goes up like that. And that pink graph is a real rough sketch of what a solution curve would look like if it passed through that particular point, and that certainly looks like a cubic function. Now let's take a look at part C, where it wants an equation of a tangent line to y equals f of x passing through 1, 2. So a linearization or tangent line. So L of x is going to equal f at a plus f prime of a times x minus a. That's a review of the line tangent, the linearization. So specifically now L of x, our line tangent, is going to equal the f of 1 plus f prime of 1 times x minus 1. Continuing further, plugging in the specific values, f of 1 is 2 plus f prime of 1 is 3 times 1, so that's going to be 3 times x minus 1. There we go. That is the equation of the line tangent to the curve at 1, 2. So now we're going to look at part D, where it says approximate the value of the function at 2. So f of 2 is what we desire, and we're going to approximate it with the linear approximation at 2, and then I'll plug that into my line tangent equation. 2 plus 3 times 2 minus 1, so that's 2 plus 3 equals 5. So let's come over and show that on our diagram. The line tangent centered here at 1, 2, and we know that's going to go at 2, 5 here, so that'll help me construct with a slope of 3. 1, 2, 3, 1 here also. So my line tangent is going to go, I'll try my best to make this straight, and you see it's tangent to the curve. Okay, that's about as straight as I'm going to get on this particular device, but that's the line tangent, and the line tangent, I can hardly see that, L of 2 is equal to 5. Now in part E, we're asked to find the general solution, so I'm going to separate the variables. dy equals 3x squared dx, and I'm going to integrate both sides. That's going to leave me with y equals x cubed plus c. So that's the general solution. So all the solutions that would fit this slope field have the form y equals x cubed plus c, and our pink function that we drew earlier certainly fits that model of a cubic. And in this case, it looks like the plus c would be 1. But what we're going to do part F now is solve and find the particular solution that goes through the point 1, 2. So 2 equals 1 cubed plus c. Therefore, c must equal 1, as I suspected, and so y equals x cubed plus 1 is the particular solution. That is the graph that we drew in pink. So in fact, I can update this graph in pink and say, well, at 2, it's going to be 8 plus 1 is 9, so that's going to go through this point up here. So if I extend my function now, well, it got real steep, and it passed through that point and came down. Indeed, passed through here with a slope of 0, and that's going to keep going down over here. Alright, and then in part G, we do just as I did with my point. I'll say that f of 2 is equal to y of 2, which is 2 cubed plus 1, which equals 9. So here, at this point, the function at 2 equals 9. When we used approximation, we were all the way down here, so that was off a bit. L of 2 was equal to 5. So that was 4 units off by using a linear approximation. Now we're going to look at part H. And part H has a little bit of a different criteria. The solution curve has to pass through the point -1, 5. At any rate, we want to find d squared y dx squared. Now we're going to pretend that I don't know what the function would be that passes through -1, 5. I'm not going to spend the time doing that. So I'm going to simply say that the second derivative would be the derivative with respect to x of dy dx. And so that's going to be the derivative with respect to x of 3x squared, which comes out to be simply 6x. I'm first going to say that dy dx at this particular point, only depending on x, but dy dx is going to be 3 times -1 squared, so that's going to be simply 3. But the second derivative, dy squared dx squared, at, still depending on only x equals -1, is going to be 6 times -1, which is -6. So why is that value important? The -6? Well, that's certainly less than 0, and if you recall, that's an indication of the concavity of the solution curve at the point -1, 5. So we're going to say that the graph of f, with again the condition going through -1, 5, but the graph of f is concave down at that point, -1, 5. So now what are the implications of the concavity for linear approximations? we conclude, therefore, linear approximations that are centered at x equals -1 will overestimate f for x values near the -1. So if we look at the curve, which would be concave down at -5, 1, so concave down at the point, then a linear approximation, which would be tangent, would be overestimating. So it would overestimate for values, let's say, close to -1 here, close to -1 here. The linear approximation overestimates. Now, sometimes the curve can change quite drastically and quickly, so that's why we want to say this near, because it could change concavity as it moves outward. Example number 2, y equals f of x, a solution curve that will pass through the point 1, -1. It has the derivative dy dx equals -x over y. Notice that this slope depends not only on x but also y, so we can write it f prime of xy equals this -x over y. And if you've been watching the videos in the series, you will recognize this particular differential equation. We're going to graph the slope field now. I'm going to start with some points that are not odd or weird. I'm going to start with f prime at the point 1, 2. And if I plug 1 and 2 into my slope, then I will get -1/2. If I plug in f prime at 2, 2, I will get 1. F prime at 1, 1, I will get -1. F prime at 2, 1, I will get 2. I'm looking in the first quadrant for those particular slope slashes. Alright, so at 1, 2, the slope is -1/2, down 1 over 2, so less steep, something of that nature. At 1, 1, the slope is a -1, so a little bit more steep, but in the negative direction. At the point 2, 2, the slope is supposed to be, I wrote 1, it's supposed to be -1. Let me fix that. There we go. So the slope of -1. The slope at 2, 1 should be -2. Looks like I was rushing here. -2. Let's draw that steeper. So down 2 over 1. I just want to make sure it's steeper than the -1. Let's take a look at some points in the fourth quadrant. So f prime of 1, -1, f prime at 1, -2, f prime at 2, -1, f prime at 2, -2. Those values 1, 1/2, 2, and 1. Again, I'm plugging that in to my slope formula. And coming back over, we're going to try to draw this a little bit better. This one up here should have been more like by -1. I have it a little steeper than that. So let's see here. So at 1, -1, the slope is 1. At 2, -2, the slope is 1. At 2, 1, the slope was 2, so steep. That's steeper. Then at 1, -2, slope was less steep at 1/2, like that. I went ahead and filled in some of the other slope slashes to represent the 2 plus or minus 2 plus or minus 1/2. Some of the specialty ones come when f prime at 0, 0. You cannot have 0 over 0. It's an indeterminate form. And with the indeterminate, we do not put any slash. That's different than saying f prime at 0 as long as y is not equal to 0. You can see that if the numerator is 0, then all of the slopes will be 0, showing that with our horizontal slashes, like that. Then for f prime at x is not equal to 0, but y is equal to 0, then those are going to be undefined. Now those do get slashes, they get vertical slashes. So vertical slash here, vertical slash here, vertical slash here, and a vertical slash here. And it certainly looks like circles would lay on top of this slope field. In part B, we have to draw a function solution that passes through the point 1, -1. The fact that it has to be a function prevents us from doing a full circle, because a full circle would not be a function. I have to follow the slope field, which is going to pass through here and curve back up and have a vertical line tangent there. It's going to come over, have a slope of 0. I'm following the contour of this, come around and do that. It cannot be a full circle because a full circle would not be a function. So I have here a semicircle for my solution that passes through the point 1, -1. Part C wants the linear approximation. Now the linear approximation is going to be slightly different because the slope will depend on an x and a y. So we'll write this as generically f of a plus f prime of a and b times x minus a. That's the equation of the tangent line. So L of x is equal to here f of 1 plus f prime of 1 -1 x minus 1. Let's keep filling in specifics. So this is going to be -1 plus, now the slope at 1, -1 will be +1 x minus 1. There's the equation. I just want to write it without that coefficient. So that's the equation of the line tangent, the linearization. In part D, we want to approximate f at 0 using the line tangent. So that's going to be L at 0, which is -1 plus -1. That comes out to be -2. Let us illustrate that, please. Here, a line tangent is going to have an equation that goes like this. That's about as good as it gets with this technology, but I like it. That's supposed to be straight and touching the curve at one point. Here at the point 1, -1. If we use the tangent to approximate the function at 0, then it's going to give us this value down here of -2. Part E, we're going to solve the differential equation, first getting the general solution, separate the variables. We have y dy equals -x dx, separated the variables, take the integral of both sides. That's going to give us y squared over 2 plus x squared over 2 equals c. And if I solve for y is going to equal plus or minus the square root of c minus x squared. Part F wants us to find the particular solution that passes through the point 1, -1. So -1 equals plus or minus the square root of c minus 1. Now the plus or minus is determined now because we know our value of y has to be negative, so it has to be the negative variety, and c has to equal 2 in this case. So our final particular equation is negative radical 2 minus x squared, which is the semicircle that I drew earlier in pink. Here it is. That is a semicircle with the equation y equals negative radical 2 minus x squared. In part G, f of 0 is equal to y of 0, which is negative radical 2. Let's see if we can't show that highlighted over here. That's here, negative radical 2 versus negative 2 that we got with the linear approximation. Finally, in part H, we're going to find the second derivative again, d squared y dx squared, which is the derivative with respect to x of dy dx, which is the derivative with respect to x of negative x over y. I'm going to employ the quotient rule. Bottom times the derivative of the top minus top, minus minus becomes a plus. Derivative of the bottom is dy dx all over the bottom squared. Dy dx at the point, let's see, it changes its criteria now. Like the other one, we want to look at a curve that passes through -1, 5. Dy dx at that depends on both the x and the y. Will come out to be positive 1/5. Now we're going to find d squared y dx squared at x equals -1, y equals 5, but also at dy dx equals 1/5. So that's going to equal 5 times -1 plus -1 times 1/5 all over 25, which simplifies to -26 over 125. That number is important because it is less than 0. So the graph of f is concave down at the point -1, 5, and therefore linear approximation centered at -1, 5 will overestimate f for x values near the x equals -1. Example number 3, dy dx equals x plus y. We're going to make the slope field. I'm going to go below down here to do it. I'm going to walk down the center column of points. So let's do f prime at 0, 2. This is pretty easy because it's just the sum of the xy, so that's going to be 2. F prime at 0, 1 is 1. F prime at 0, 0 is equal to 0. F prime at 0, -1, -1. F prime 0, -2, -2. Let's go to the next column to the right. F prime 1, 2, 3. F prime 1, 1 is 2. So on and so forth. And again, it's just a sum, so this one's pretty easy to evaluate. Alright, like that. So let's begin to do the slope field over here. At 0, 2, it's 2, so it's a little bit steeper. At 0, 1, it's 1. And then it goes to 0. Then we go to -1. And then to -2, steeper, negative. The next row we have even steeper still. And then steeper, or steep, slope of 1, slope of 0, slope of -1. Okay, I've created the rest of the slope field. You might notice that along the diagonals that they're the same slope. So along this diagonal they're all equal to 2, while along this diagonal they're all equal to 1. Now we have to draw two different solution curves. Y equals h of x, which is going to go through 0, 2. 0, 2 is here, this point, and I'm going to follow the slope down. It looks like it's going to be 0 and then come up and have that feature here. Alright, and then the other one, y equals g of x, goes through 0, 1. 0, -1, and I see here that that's going to follow this slope here of -1 all the way down. So that one appears to be linear. Part D wants a linearization line tangent to y equals f of x centered at -2, 2. So again we have L of x equals f of -2 plus f prime at -2, 2. x minus a, or x plus 2. So we have L of x equals 2 plus 0 times x plus 2. Notice that the slope is 0, leading to L of x equals just 2. A line, horizontal line tangent. Consequently, f of -1 is approximately the line tangent at -1, which will equal, obviously, 2. Lastly, part f, the derivative of the derivative is going to equal the derivative of x plus y, which will equal 1 plus dy dx. The question calls for what's happening at the point -1, 5, so dy dx at the point x equals -1, y equals 5 is going to be -1 plus 5, which equals 4. d squared y dx squared, x equals -1, y equals 5, and dy dx equals the 4 is going to result in 1 plus the 4, which equals 5. Once again, that's important because it's positive, and the graph of f is concave up at the point -1, 5. Therefore, linear approximations centered at -1, 5 will underestimate f for x values near -1. Concave up looks like this. If I had a linear approximation, those points along the line will be under the curve. I would like to emphasize that in example 3 here, where dy dx equals x plus y, you cannot separate the variables. So in this particular course, you do not have the skills needed to solve the differential equation. Not able to separate the variables here. Can't get y dy, x dx on their own sides.